Right, this is the second part of the shifting equilibrium, or Le Chatelier's principle. Okay, so same packet as before, and this is just a continuation. So up to this point, we've discussed how a change in concentration of either reactant or product can affect the equilibrium position. We've discussed how a change in the volume of a container can affect the equilibrium position, and we've discussed how adding a gas and thus changing the mole fractions can change the equilibrium position. Okay, so we have a couple things left to talk about. And that first one is the effect of temperature changes. Okay, so if you have a bullet point on your paper that says, in order to apply Le Chatelier's principle, we must treat heat as if it were a reactant or a product. And then it simplifies this discussion by quite a bit. Okay, so of course we know from thermochem discussions that we have two types of reactions. We have endothermic, we have exothermic reactions. And so when we find out about the thermodynamic nature of a reaction, it's best to include heat as either a reactant or a product, and it makes this discussion much easier. So obviously, if a reaction is endo, we know that heat goes in, which means heat would be considered a reactant. So I always add heat to my reactant side of my equation. It's a bad choice of color. I apologize. And then I know exothermic means heat is released, and so that would mean that heat is a product. So if it's exothermic, I would add heat to the product side of my equation. From there, once we do that, we can almost treat, let me write this. So once we have identified if heat is either a reactant or a product, we can almost treat heat like we did changing the concentration of something, of reactant or a product. So see, this is going to be easier to explain verbally than in writing. So you might just kind of want to listen to this. So for example, if I know I have an endothermic reaction and heat is a reactant, okay, then if I raise the temperature of the reaction, what I'm effectively doing is adding heat, okay, and if I'm adding heat to my reactant side, then Le Chatelier's principle says I need to use that up to relieve the stress, so the reaction's going to shift to the right. Okay, the opposite would be true in an exothermic reaction if I increase the temperature, because heat's a product. So if I added heat in an exothermic reaction, it would be like giving it more product, and to counterbalance that stress, the reaction would shift to the left to use up that heat. We could also talk about by lowering the temperature of a reaction. Okay, so if it's endo and you lower the temperature, it means like you're removing heat, okay, and you would need to make up for that heat, so you would shift it to the left. And then in an exo, if you removed heat, right, if we're going the other way now, or you lowered the temperature, that would cause the reaction to shift to the right to replace that heat. So that is not worth memorizing, and that is not worth like doing 4 bullet points in terms of what happens. I think this is kind of the takeaway, that as long as we can put heat into my reaction, then I can treat it almost as if it were, a concentration of something, okay, just like we learned before. So that's the easiest way to do it. And yeah, so let's look at a problem. And I want you, so we're right here, okay, under this where it says consider the equilibrium. And if you would cross out a letter C for me, it's a bad question. I don't like it. I actually have an error in how that was typed, so we're going to just cross out C, okay? And I can tell you why. I think I will tell you why, but I'll tell you why after this question. Okay. All right, so we're given a reaction. It looks like this. We're told the delta H, and I have, several questions about it. Which way is it going to shift? Okay, if these things happen. So A is if I add N2O4. B is if NO2 is removed. C I'm not doing, but we'll talk about it. D is the volume of the container is increased. And E is temp is decreased. Okay, so let's go through this together. All right, so we actually cover all of these here that we've talked about so far. We're covering changing concentration, changing volume, and thus changing pressure, and then temperature. So, okay, if N2O4 is added, so if I have extra N2O4, equilibrium will be disrupted. I need to use it up, so it's going to shift to the right. So the answer for part A would be that it shifts to the right. B, NO2 is removed. So if I took some NO2 out, I would need to replace that. So it's also going to shift to the right, but for a different reason. In this case, that the NO2 would need to be replaced. Okay, C, skipping. D, if I increase the volume of my container, which means that the total pressure in the container is going to decrease. So pressure's too low. I need to offset that by increasing the pressure. So it's going to shift to the side with more moles of gas. So it would also shift right. A lot of rights here in a row. And then the last one, what happens if the temperature is decreased? So here's where it's important that we take this and add in heat to my reaction. I always recommend you do this. So delta H in this case is positive. Endothermic, heat's a reactant. So nothing wrong with coming up here and writing in the heat. So if temperature is decreased, so if I take heat away, all right, it's just like taking away a reactant. And so if I take that heat away, I need to replace that heat. So in this case, the reaction is going to shift left. Okay. The reason why question C was no good, and this is really important, and we'll make sure we address this on the takeaway, is that it says the total pressure is increased by the addition of N2. Well, when I talked about adding another gas in the last video, we had I don't know that I ever came out and said this, but that takes into account and makes an assumption that the total pressure in the container doesn't change. Because if the total pressure changes, this whole thing goes, it's just a mess. So in that case, in the prior video, my total pressure did not change, but my mole fractions changed, which meant my partial pressures changed, but my total pressure did not. So that's why I don't like question C in this case. It was a mistake. It was poorly worded, and so we threw it out. All right. So next topic, the effect of catalyst. Okay, so if you remember from the last chapter, a catalyst increases reaction speed by lowering activation energy, right? Lowers the hill, okay, so to speak. But the big takeaway in, and that's not a Q, oh my gosh, that's EA. So a catalyst increases the reaction speed by lowering activation energy, but does not shift the equilibrium position. Okay, so a catalyst, you can add a catalyst all day. It'll speed up your reaction, just like an inhibitor would slow down your reaction, but it will not cause the equilibrium position to shift. Okay, so watch out for that. Be aware of that when it comes to questions that ask, what happens to the equilibrium position when a catalyst is added? It's a trick question. Nothing happens to the equilibrium position. Okay, so there's a kind of one follow practice question, so let's do that together. PCl3 plus Cl2. Okay, so letter A, how's this going to shift in, so we'll just do right, left, like that kind of stuff. So letter A, Cl2 is removed. So you take away Cl2, you need to remake Cl2, so it's going to shift to the left. Letter B, the temperature is decreased. Okay, so I need to take into account my delta H. It's exo, so heat's over here. So temperature decreases, so I don't have enough heat anymore. I need to make more heat, so it's going to shift to the right. Remember, it's all about counteracting the change. Letter C, the volume of the container is increased. So volume increases, pressure decreases. Pressure's too low, we need to make more pressure, so it's going to shift to the side with 2 moles of gas instead of only 1 mole. So that would be left. Letter D, PCl3 is added. So I add some more reactant. I have too much of this, I need to use it up. So it's going to shift to the right. Letter E, a solid catalyst is added. So we just talked about that a catalyst has no shift on the equilibrium position. So that's a kind of your trick question there. So there would be no shift in letter E. And letter F says into gas is added to the container. So this is what I just touched on. If you add into gas to the container, it's not in the original reaction, but assuming it doesn't change the total pressure, it means that the mole fractions of these 3 gases decrease, their partial pressures decrease. So the partial pressures of all my gases are too low. I need to make up for that. I need to raise the total pressure to account for the lower partial pressures of the 3 gases in my reaction, which means it would shift to the side with more moles, which would be the left. Okay? And technically, that's the end of the notes for this section, but I kind of left something off. And so, since this video is not super long, if you just want to flip to the back and kind of add your own heading, we have, technically, there's one more that can affect equilibrium shifting, and that is the effect of either dilution or evaporation. Okay, and this is for aqueous reactions. So we'll do 4 aqueous reactions. Okay, so whether we dilute something or whether we let water evaporate, if it's an aqueous reaction, that change in H2O can cause a shift in the equilibrium. So we'll write that change in H2O causes equilibrium shift. Okay, so here's my example. And again, this only works for an aqueous reaction, right? If it was a gas reaction, that doesn't, diluting something doesn't make any sense. Okay, so keep that in mind. We're talking an all aqueous reaction. Adding water or evaporating water will cause your equilibrium position to shift because there's essentially water in that reaction, right? Water is like the medium or whatnot. Okay, so let's say we add H2O to this, which would be a dilution, right? So we have some beaker, this reaction's at equilibrium, and I dump some more water in it. So I upset the equilibrium. It's too dilute, okay? There's not enough of your solute, so to speak. So I need to increase the amount of solute that is present. So the reaction will shift to the side with more aqueous species. So in this case, it would shift to the left because there's 2 things versus 1. Okay, and it's making up for the fact that it's too dilute, right? So we're increasing that. We're creating more, it's a 2 for 1 deal. So we're going to shift this way to make more. And then, of course, you might guess that the opposite is true is if H2O is removed, and that would only pretty much happen through evaporation. Then my solution is too concentrated, and the reaction will shift to the side with fewer aqueous species, and in this reaction, that would be to the right. Okay, so these kinds of questions are infamous in the multiple choice section of the AP exam, talking about if these things happened, which way would the reaction shift? Okay, so that is shifting equilibrium and Le Chatelier's principle of how changing concentration, changing volume, changing pressure, changing temperature, adding a catalyst, goodness, and diluting or evaporating water from an aqueous solution can shift the equilibrium position.